In this video, I'm going to give an example of mass action kinetics. Mass action kinetics is a way of describing chemicals reacting in solution. Usually the solvent is water, although other solvents are possible as well. The chemical equation gives a list of reactants on one side and a list of products on the other side. And there's a constant sometimes written above the arrow that indicates the constant of proportionality. So when I say reactions happen at a rate jointly proportional to the concentration of the reactants, what that means is that the rate of the reaction as shown here is K, that's the constant of proportionality, times R1 times R2, and so on. Now, as to what do you do with that, you keep track of how many units of each reactant and product are created or consumed by the reaction, and you add or subtract terms like this when formulating the differential equations for those concentrations. And that's a 2. So, as an example, on page 39 of the Strogatz book, there's a problem 2.3.2 about an auto catalyst. And here's the reaction that is written. Oops, that's 2 x's. So first, to unpack this, this is really a shorthand way of writing 2 reactions. The first is sometimes thought of as the forward reaction, and it says that an A molecule of type A comes into contact with a molecule of type X, and after they've interacted, there are 2 X's, and this happens at a rate K1. With a rate constant K1. So what that means is that the A has effectively been turned into another X by interacting with the X here. Then there's a back reaction which runs in reverse. So this says that sometimes 2 X's can bump into each other. One of them remains unchanged, but the other one turns back into an A. Usually what's going on is that the forward reaction happens at a greater speed or is somehow more likely than the back reaction. So this is essentially a correction to the dynamics given by the forward equation. So what we need to formulate differential equations, well, let me first set up the variables. I'm going to let little x be the concentration of species X, which is sometimes written as brackets around an X in chemistry notation. And then I'm going to let A be the concentration of A, and again in bracket notation, that looks something like that. To build the differential equation, let me start with this. We need to have rate of change equations for the concentration of X and the concentration of A. Looking at the forward equation, what you can see is that the reactants are an A and an X, which means that the reaction will contribute terms that look like A times X to the 2 differential equations. Now counting, on the reactant side there's 1 X, and on the product side there are 2 X's. So we have gained a total of 1 X here, Oh, I've run out of room. Let me move this over. So plus AX. If you look at the A's, there's one A in the reactants, and there are no A's on the other side. So we have lost 1 unit of A, and we need a constant of proportionality on these terms. So that's where the K1 comes from. So that's incorporating the forward reaction into the differential equations. Incorporating the back reaction, the reactant side has two x's bumping into each other. That means that what we need is a term that is proportional to x times x. And I'll just write it as x times x. That's because two x's have to bump into each other for this reaction to take place. On the reactant side, there are two x's, but on the product side, there's only one x. That means that there's a loss of one x. So we have an x and we have lost an x. There are no A's on the reactant side, but there is an A on the product side. That means that we have produced 1 unit of A. Then the constant of proportionality is given there. So that's how to translate the forward and backward reactions into terms in these differential equations. If you now clean this up, you'll see, you'll see that x dot is k1 ax minus k minus 1 x squared, and a dot is minus k1 ax plus k minus 1 x squared. The problem in the book focuses on just the x equation and says, let's consider this in the case where there is so much of A floating around that it doesn't change the concentration very much if a little bit is consumed by this reaction. And the problem then is to work out what the dynamics of X are, holding A constant. But that's the derivation. So again, to summarize what's happened, for mass action kinetics, you assume that you have a well-mixed solution. You keep track of the concentrations of all of the reactants. So there's over here, reactants, and the products. The reaction happens at a rate jointly proportional to the concentration of the reactants. And then to figure out how to work that into the differential equation, you have to figure out what's gained and what's lost each time the reaction happens. You put the gains and losses in and put in reaction rates that have terms that are proportional to the concentration of the reactants, and a constant of proportionality that's something you just have to find experimentally. And there you go. So that is mass action kinetics. This is also sometimes used in population models where you imagine, say, that you've got predators and prey in an environment, and when a predator encounters a prey individual, sometimes the predator kills the prey and eats it, and there's some constant of proportionality, and then that gives you a term in a differential equation. And that's sort of appropriate if you have large populations, essentially well mixed in whatever their spatial domain is. So you'll see this in a lot of different population dynamics as well. Sometimes at low concentrations, it's not really possible to use mass action kinetics. Sometimes you will have to modify the dynamics a little bit. That sometimes happens when you're working on the scale of a single cell or maybe even part of a cell, and there's only a few molecules of the types of interest. But if you've got a nice big solution, this is a reasonable way to set up the differential equations for the chemical reactions.